Hello, good evening, everyone. Okay, so this is the Week 7, and I hope you have watched the video. Any specific doubt in you have in Week 7? Any clarification? Am I audible? Can anyone confirm? Okay, Siddharth. Okay,
Yes,
fine.
sir.
Okay, any specific doubt in Week 7 you have? As this is the Week 7 running, Week 6 is done. Okay. Okay, so if no doubt, then we will start like as a summary of the week. Okay, and we will discuss the topics. If you have any specific doubt in any topic, you can ask in between. Okay, it's fine. Okay, let me share my screen first. So as Week 7, now from Week 7 onwards, so till now you have learned different type of data structures. Okay, so graph data structure, tree data structure. From Week 7, we are also discussing algorithm design techniques. Okay, different strategy to design algorithms. So that there are three algorithm design techniques we are covering in the course. First is greedy algorithm. Second is divide and conquer. Third is dynamic programming (DP). Okay, so Week 7 is where from we are starting the first greedy algorithm techniques. But one topic is left from the Week 6, so that is the binary search tree, which we have started in Week 6, but that is not completed. We haven't discussed that how we can benefit from the binary search tree. Okay, how we can take the advantage of that operations on the binary search tree. So that is now continue in the Week 7. So in here in the Week 7, we are continuing with the binary search tree and the different version of that as a balanced search tree. Okay. So in this we are learning an algorithms AVL tree. Okay. So let's start with this, and we'll discuss that how this algorithm works and how we get the benefits of the binary search tree operations. Okay, so let's start with first small recap of binary search tree. So I hope you know the operations of the binary search tree, condition of the binary search tree. So binary search tree is a binary tree. First thing, okay. So we can contain maximum two children of any node. So that is the condition of the binary search tree. It is also a binary tree. But here we have some specific rule. Any node. So any node, suppose if you are taking like A, so there is a two node. Generally, we said that as a left node and right node. Okay. So suppose this is the left one and this is the right one. Okay, so the condition is left child should always be smaller than the parent node. Okay, what is the parent node we have? And right child will always should be greater than to the parent node. So this is the condition between this pair of parent and child, left child and right child. And this condition is satisfied with every subtree of the tree. Okay, suppose we have one more label like here this is the left child and this is the right child of this. So same rule will be applied on this part. Okay, as well as all the nodes which are coming in the left subtree should be smaller than to the that had that node which is that subtree is connected on the left. Okay, so all nodes which are coming on the left subtree, that will be smaller than to the that parent node. Okay, similarly all the nodes which are coming on the right subtree will be greater than to this. So this rules is applied on the binary search tree, and we utilize this for contain the data, and later we can search the data efficiently. But here the problem is, if with only this definition, suppose we are getting some data to insert in our data structure of this binary search tree. But there is a situation that suppose I'm getting the order like this. So like we have the 10, 12 and 15, 20, 30, 50, like this. Okay, suppose we have this number of elements, and if we create a binary search tree for this sequence, so we are getting the elements one by one and we are inserting that into a binary search tree. So I hope you know that how to insert into the binary search tree. So first node will be created as a root node, because currently this is empty tree, so we will insert it as a root node. After that, next node 12, we will always start comparison from the root node, and based on the value to the current node, we will just move our direction, okay, to insert. So 12 is greater than to the 10, so we will check the right child, but there is no right child, so we will add as a right child of this 10, this 12. Okay, same 15, we will always start from the root node when we are going to insert. So 15 is greater than 10. Okay, we will move to the right. If right child is available, again we will compare, okay, to that. So 15 is greater than 12, then we will again check for the right, but now right child is not available, so that is the empty place. We will insert our new element. So 15 will be insert here. So 20 again from the 10. So do not directly put insert, okay, that will create a wrong binary search tree. There is chance. So always start from the top if you are creating binary search tree, and then move according to the value comparison. So 20 is greater than 10, move to right, right child is available, again compare. So 20 is greater than 12, again move to right, so right child is still available. So 20 is greater than 15, so again now the empty place, so add this 20. So now you are getting this type of tree. By this is also a binary search tree like this, and there is no advantage of this. Suppose we have created one binary search tree and we are getting this type of structure. So this is like as a like an array, okay, or just like a linear data structure which is stored in the list. This is equivalent to your linked list if we have the element like this, okay, 15, 20 and 30 and 50, like this. Okay, so if you want to search any element, so you have to traverse all the element from the root. Suppose if you want to search 50, you have to traverse from the 10, then 12, then 15, then 20, then 30, then 50. Then you can identify that this 50 is exist in this. So means you here you have to work completely on n element. So means you have to compare all n elements which are available in this way to identify your searching element. So this operation is overall n order of n operation. Okay, same things like searching is there, deletion and insertion operation also become worst situation. So this is just like a worst case where your tree is connected like this, and this tree's height is actually equal to the number of nodes. Okay, so number of node is n, same height is also equal to n. Okay, because each level side, like each node is come on the next level. So this height is actually equal to the n. So here we are not getting any advantage of this binary search tree, and in this arrangement, so we require a balanced binary search tree. Okay, so we require a balanced binary search tree, so if we can reduce the height of this tree. Okay, because this searching, insertion and deletion operation is depends on the height. So how much height you have, you can perform your operation in the same ratio of height. So if you can reduce the height to the minimum, so then you will get a efficient operation on that. So that is balance thing actually. So balance is just like we have the similar height on the both left and right subtree, like this. So here you can see this is also a 7 node, and above one is 6. If we also connect one more, suppose this is also 7. Okay, so here the height is 7, but if our elements are arranged in this way, okay, so here height is 3. Okay, here height is 3. So any element you can search in 3 comparison, and here you can you have to search 7. So this is just equivalent to your log n thing, log base log n. Okay, so me suppose just take a big example on this. So suppose if you have n equal to 1024, so this is the n. If you make this type of tree structure in worst case situation, so height will also be 1024. But if your tree is balanced, so this is log to 1024, and that is equal to 10. Okay, so means 10 height of 10, you will create a balanced tree, and any element you can search in 10 comparison only. So here you can see the totally difference in the efficiency. In this you have to compare 1024 element to search. Here you have to compare only 10 element to search. So when we have large data, so there is a clearly advantage of this. Okay, so now AVL tree comes in the picture. So we want to make this tree as a balanced tree. So we want to create a like, approx similar height on the left or right subtree. We are not guaranteed that we will create a exact same height. Okay, but there is a rule for the AVL tree that if our height difference is 1 or 0, then we will consider as a balance. But if height difference is more than 1, so height difference is just like a suppose this is the tree and this is the left subtree of this. Okay, and this is the right subtree. Okay, and just take the height of this subtree and this subtree. So height of this subtree is actually just identify the number of nodes in the longest path from root node to any leaf nodes. So this is 1, 2, 3. Okay, so 3 is the height for this subtree, and this side height of this is 2. Okay, so 2. So difference of this left left subtree and right subtree is 3 minus 2. This is 1. So we will consider this as a balanced tree. Okay, but if we have suppose one more connection on this left side, so now height is 4 of this subtree, and right subtree height is 2. So now 4 minus 2 is 2. So here we will not consider this as a balanced tree. So according to the AVL, so that is called as a balance factor. Okay, so balance factor, that is actually HL minus HR. Okay, this difference should always be less than equal to 1. So this is the rule for balance factor. So balance factor we calculate for each node. Okay, and that is just a absolute difference of left subtree height and right subtree height. That should be less than equal to 1. Then this is fine. That means it is our tree is balanced. If it add for any node, if this balance factor is in like not equal to or less than 1, it increase to the 2 or 3 like this, so then we will consider as a unbalanced, and then we will apply the rotations on the tree. Okay, so some rotations we will apply to make tree balance. So this is the idea of that AVL tree concept. So first thing, this should be clear, what is this balance factor. Okay, so let's take the example of balance factor. So suppose I am just creating a different version. So suppose uh, so suppose this is a single node. What is the balance factor for this? Okay, so balance factor for this, because there is no subtree on the left, no subtree on the right, so means zero height for that. Empty tree is considered as a zero height. So zero height of the left subtree, on the right subtree is also 0. So mod difference is 0 minus 0 equal to 0. Okay, so means this single node will be considered as a balanced. Suppose we have the another version like tree with 2 nodes. Okay, so here we are calculating the balance factor for this lower one. So there is no left subtree connected on the this left and right. Okay, so this is the similar condition like we have discussed previously. So 0 minus 0. So balance factor for this node is 0. Now calculate the balance factor for above node. So check, this is the left subtree, but there is no right subtree. So left subtree have single node height is considered as a 1, and right subtree is empty, so there is height is 0. So difference is 1 minus 0, so that is 1. So left balance factor is calculated like this. So this is the 0 for leaf node, and above node is 1. So still this is the balanced condition. Suppose we have like this. Okay, now balance factor for all leaf. Now you can remember that all leaf node balance factor is 0, because there is no left subtree, no right subtree. So 0 for this, 0 for this. Now balance factor for the above node. So this is the one height tree, this is the one height tree. Okay, so 1 minus 1, this is also 0. So this is also considered as a balanced. And let's make more. Okay. So now see this type of example. Let calculates the balance factor for each node. Okay. So leaf node is 0. So leaf, this is leaf, this is leaf, 0 balance factor for each. Now the balance factor for this. Okay. So balance factor for this left is 0, right is 1. Okay. We are not counting the number of nodes. Okay. We are counting the height of this. So this is the single node tree. So that is the height is 1. So 0 minus 1 is 1. We are writing the absolute difference. Okay. So this is the that balance factor for this node. Now calculate the this one. So this is the one tree on the left subtree, height is 1, and this side this is the right subtree. Okay, so the height of this tree is 2. Okay, so this is the height of so 1 minus 2, that 1 minus 2 is equal to 1 again. Now calculate the for this. So here this is the left subtree and this is the right subtree. So what is the height of left subtree here? So this is just like a part of this. Okay, this. So here this is the root node for this tree, and what is the longest path to the leaf node? So there is a one path is this one, and another path is this one to leaf. So in the longest path, how many nodes are coming in that path? Okay, so this is the 1, 2, 3. Another path is 1 and 2. So we always take the maximum number of nodes as a height. Okay, so 3 is coming in this. So 3 is the height of this overall. And this side 1 is the height. Only single node is like I said, that tree. Okay, so 3 minus 1, absolute difference is 2. So this is you are getting balance factor 2, means this tree is not balanced. At any point for any node, if this balance factor is like goes out to the range of 1, okay, so like more than 1, okay, so then that we will consider as a unbalanced, and then we will apply the rotations. Okay, so I hope this is clear. Balance factor things, how we are calculating the balance factor for each node. Okay, Joe, I'm telling one example more, so just tell me the balance factor for that. Okay, I'm giving the name.
So in the previous one, is this 4 minus 1 or 3 minus 1?
3 minus 1. As I mentioned that we are not counting the nodes in the tree. We are counting the height
Oh,
of.
got it.
Okay, so height is the maximum. So there are two paths in there in this
So
tree.
height is also 4 na here if we'll count.
Sorry.
If we'll count, then height is also 4.
No, no. How the height is 4? We are calculating the only height of this subtree without including this. Okay. So this is the number of node if you count 1, 2, 3.
Okay, thank you.
Okay. So height we are considering we are taking as a empty tree height. There's no node, 0 height. Okay. If single node is there, then 1 height. Okay. This is just like a base case. And after that, we will take the elements, that longest path. Okay, like this. So here for this tree height is like this is the longest path. Okay. This is the longest path. So how many nodes are coming in this path? So that is like a 3. Okay. In this way. So like I've mentioned this A, B, C, D, E, F, G, H, I. Okay. So just tell me okay, I'm mentioning that leaf nodes all have the balance factor value 0. Okay, tell me the height balance factor for H.
So 1.
1. Okay, you can write in the comment also. Okay, so the balance factor for H is 1. Okay, this is correct. Okay, tell me the balance factor for E.
It's also said
1.
1.
1.
This is 1, correct. Okay, so height of this left subtree is 1 and height of the right subtree is 2. So 1 minus 2 is 1. Okay, so now the balance factor for B,
1,
1.
1. Okay, so 1 minus 0, 1. Balance factor for D,
2,
yes. So here this is the left subtree, so 3 height. Okay, so 1, 2, 3. This is the longest path, and this side 1. So 3 minus 1, 2. Okay. Balance factor for A,
2,
yes. Okay, so here this is the subtree. So 2 height for this, and this side this is the complete subtree. So 1, 2, 3, 4. Okay, so this is the longest path. So 4 node contains. So 2 minus 4, that is the mode difference. So this is 2. Okay, so this is the balance factor calculation. Okay, so first this should be very clear. And condition for unbalanced and unbalanced is if t is balanced, if the height this balance factor value is greater than 1. Okay, otherwise the tree is balanced. Okay, so now comes to the rotation part. So this is the first thing. We will create a binary search tree in the same way as we are creating as a normal binary search tree. So we will get one sequence, and after that we will create a binary search tree. But every insertion we will calculate the balance factor, and once the balance factor is become more than 1, we will apply the rotation. And what type of rotations are there? So there are 4 type of rotations in general. So first is left left rotation, second is r rotation, third is l-r rotation, left right, and fourth is right left, this type of rotations. Okay, so these are the very common 4 type of rotations are there. And what are these rotations? Okay, just understand this. So suppose if we have the order of insertion like 10, 20, not like this, 10, 20. So once we are discussing first left left, so 10, 5, and 2. Okay, suppose we are getting this type of inserting order of the element, so we will just create a binary search tree for this. First we will insert 10. Okay, 10, this become a root. Now we will calculate the balance factor for this, so this is 0. So this is the step by step process. At every insertion we will calculate the balance factor from the new node position to the root node. Okay, each element. So now this is the 10, balance factor is 0. Okay, this is fine, this is balanced. Okay, now we will insert 5 into this. So 5 is smaller than 10, so that should be added into the left side of this. So next step, we will insert 5 as a binary search tree. So now 5 is inserted. So the new inserted position to the root node, we will check the balance factor again every time. So balance factor for this is 0, and 10 is 1 minus 0, 1. Okay, so now still this is balanced. Now next node, so 2. So in the previous balanced tree we will add the new node. So 2 again, so we have already this. So now 2 is smaller than 5, is smaller than smaller than 10, is smaller than 5, then this should become here. Okay, now again check the balance factor for each. So 0 and 5, the balance factor for 5 is 1 minus 0, 1. Balance factor for 10 is 2 minus 0. Okay, 2. So we got this type of situation, and this is comes under this LL
Sir,
rotation. Hmm.
how we got that 2 means, are you subtracting from the length or what you are doing?
No, that is the formula. So balance factor is H L minus H R. This was the formula. Okay, left subtree height minus right subtree height.
So where is the right subtree height? We don't have, right?
So we are calculating for the 10. So
Hmm.
this is the left subtree, which are
Ah.
connected into the left.
Mm-hmm.
Okay, and there's nothing connected to the right. So means empty subtree.
Okay, so then
Okay,
it is 0.
so the height of this left subtree. So just
Mhm.
check from this part only. Okay, 5 and 2, this part. So what is the height of this? 2.
2.
Okay, so that is 2. And minus what is the height of empty
0.
tree?
0.
0. So 0. So we got 2. That I have written here. Okay. Yeah. So this become a unbalanced situation, and this is called as a LL condition. Okay, how this is LL actually? So which node we got more than one balance factor? So this is 10 actually. Okay, so here we got unbalanced balance factor 2. Here from we will see which side our height is greater. Which side? Left side or right side?
Left side.
Left side. Okay, so means left side height is greater from this 10. So after that, we this is the first L is representing. Okay, now we will move to the child of this 10, left child. Okay, now comes to this. From this node, again we will see which side height is more, left or right.
Left.
Then
Left.
left. Okay, so this balance factor is representing the situation of left left. Okay, so left and left means our height is increased on this direction, left left. Okay, so this is the situation for LL, and for this situation we apply a rotation, so like 10, 5 and 2. Okay, so this is the things, and this is the node which we are getting two balance factor, and we need to apply the rotation. So this is LL. Okay, here we apply the rotation on this position as a pivot position, and just rotate like this. So just pull this 10 on this position as a pivot position. Okay, so when you will just rotate like this, so this 5 will move to this 10th position, and 10 will become down to the right. So
Sir,
this will
can
become,
we say that we are just changing the position of 5 to become a root? So that why
no, this
right
will
side.
not always be, this will not always be root actually. You will see when you will perform the things
Mm-hmm.
on the tree, you will get this things will comes below in the tree as well, not always the root.
The middle element 5, that we are changing it to the top position, right?
Huh, at the, so as I mentioned that this is just like a pivot position. Okay, so here,
Like how
and
to find that? Because in
this
one
is
of
the
the
balance factor
examples
na?
are did.
So for this LL situation, which node we are getting this two balance factor, so that
Okay,
is the position.
so from the below means from the leaves to node we are traversing,
Huh.
kind of,
So
right?
this just we pull this like one node on this things, and this 5 will move to at the 10th position, and this will move to onto right position one.
Huh.
So this will become situation after this. Okay, so this pivot position was this one, so that 5 is at now 10th position, and 10 become is this right, and now 2 is just shifted to one position up.
Sir, for balancing, we are selecting the pivot position. So we will select a pivot position which is the greater, which has the greater balance
Yeah,
factor.
yeah, which is detected as a balance factor more than one.
Okay, sir.
Okay, that is the position actually. So on that position, you need to just apply a like clockwise rotation. We said that clockwise rotation in one node. So this is just like a rotation. After that rotation, we will got this type of tree, and this is now become a balance. So 5 is now become this, and 10 and 2. So now you can see all balance factor is now 0. This is also 0, and this is also 0. So in this way, we are reducing our balance factor of that node, which is become unbalanced. So now our tree become balanced. So this is the one situation. You will get this situation when you will work on the bigger example. Okay. So I am discussing all the possible situation which will come at the this balance factor mismatching things. So this is LL situation. I hope this is clear. What is this LL situation? And when you will get this LL situation, you will apply this type of rotation, one clockwise rotation. Okay. Now comes to the RR. So RR is just reverse of LL. Suppose you are getting the element like 10, 20, 50. Okay. Now you are creating the binary search tree for this 10. Okay. Is inserted as a first. Now the balance factor for this is 0. Next step 10. You will add 20. 20 is greater than 10. So it will add into right here. So now balance factor this is 0 and this is 1. Correct? And now this is also balanced. So we will add new element to this, and this is 50. So 50 is greater than 10, greater than 20. So that should be come onto this right 50. Now after that, balance factor for this is 0, this is 1, and this is 2. Okay, so left subtree height is 0, right subtree height is 2. So 0 minus 2, more difference is absolute difference is 2. So you can see now this node become unbalanced. We are getting unbalanced factor on this. So this tree is unbalanced. And now we will identify that which side we are actually getting more weight. So how we are getting this RR. Okay. So from this position, we will check first which side height is more, that is right side. Okay. Now we will move to the right child, and from the child we will see which side height is more, that again right side. Okay. So this is the RR situation. This situation we are getting for the balance factor. So now we will apply a rotation on this in the reverse way, which we have applied in the previous example. So this is R. Okay, now this is again the same pivot position, and this time we will apply a anti-clockwise rotation on this position. Okay, so now this 20 will come at the 10th position, and 10 will become left, and then 50 will come as a right. Okay, so this is the rotation. After rotation we will get the balance. Okay, so that 0 0 and 0. This is not always all 0. You will but if this balance factor 2 will reduce, actually it will become either 0 or it will become as 1. So the after rotation your tree will actually become a balance according to the AVL rule. Okay, so this is, there are two conditions. I hope this is just a one reverse of each other.
Sir, can you take an example of 5 or 6 node and then do this conversion, either left or right?
What you said, 5 4 6?
5 or 6 nodes, because 3 it's very clear that middle will go
So as I mentioned that I am just now I am discussing the one part which you will see in your example, bigger example. Okay, so because of that I am showing you this type of situation, because our every insertion happen step by. So once we will add one node, we will check our balance factor. Okay, and at that time you will see either this one condition, either of these four. Okay. Okay, so this is not like we will give the complete random tree for that and you will apply the things. This is the step by step process. Okay, at every insertion you have to check this. So now these are the two types, LL and RR. Now comes to the LR. Okay, this is the third type, LR. So suppose we have the like order 10 and 5 and 8. Okay, like this type of. So just add this 10 first as a single node. So balance factor is 0. Now 5 will be inserted into the left. Okay,
Yes, sir.
so 0 and this is become 1. Correct, still balanced. Now 10 and 5, so insert 8. So 8 is smaller than 10, move to left. Now greater than 5. Okay, so move to right. So this should become right. Okay, so now the balance factor for this is 0, this is 1, and for 10 this become a 2. Okay, here left subtree height is 2, right subtree height is 0. So 2 minus 2, 0, 2. So again we got the unbalanced things on this. So here just see what type of situation, how this is LR. So from 10 where we are getting more balance factor, so just see which side height is greater from 10. So left side. Okay, this is the first 10. Now move to the child of this. Now from left child, which side height is greater? So this is right side. Okay, so this is the situation LR. So our height is increased to left and then right. This side our height is increased from this node. So for this situation we required 2 rotations. Okay, so I'm making again here. So 10, 5 and 8. So LR. So here we required 2 rotations. So this is the 2 balance factor we got. So first rotation will be applied on the child, left child of that node, which we are getting the balance factor 10. Okay, so that means here we are getting unbalanced things, not 2. So for this left child, just go to the left child here and apply the only this part. Okay, apply the anti-clockwise rotation. Okay, consider this as a pivot position apply the anti-clockwise rotation here. So after one rotation, so this will become a 10, and this 8 will come at this 5 position, and 5 will move to one position to the left side. So like this. Okay, after one rotation. So here we just rotate like this. And after this rotation, second rotation will apply on the node which have the balance factor more than 1. Okay, so that
Clockwise.
original. This is the clockwise. Okay, so now 8 will come as a position of 10. 10 will move this side, and 5 will move this side, and now become balance. So this become a balance things. So remember that LL only one rotation, RR only one rotation, but LR or RL we require two rotation, first on the child and then on the same node. Okay, so this is the main idea of rotations of LR, and RL is just reverse of this RL. Okay, so RL is a situation like 10, 30 and 20. Okay, like this. Suppose this type of insertion happening, and so 10 will insert like this, so 0 with 10 and then 30. Okay, so this is on the right, so 0 and 1 and then 10, 30 and then 20 will come. So 20 is greater than 10, move to right, less than 30, so move to left. 20 will add here. So this is 0, this is 1 minus 0, 1, and this is 0 minus 2, so that is 2. Okay, and this is the RL situation, so means from 10 which side height is greater, so right side. Okay, and from the right child of this, which side height is greater, that is left side. So this is the RL. So for this we will apply again two rotation in the same reverse way, so 10, 30 and 20. Okay, so first rotation will be apply on this, so that is clockwise rotation. So 10 will remain as it is, that 20 will come at here and 30 will come here. Okay, second rotation will apply here, so that is anti-clockwise. So after that 20 will come at the top, and 10 and 30 like this. Okay, so now our tree will become balanced, so that's 0, 0 and 0. Okay, so no need to calculate the balance factor in middle after one rotation. Okay, so we will apply the both rotation, two rotation, then we will check, so this balance factor is reduced. So this is the always things, you will get a balance factor lower than 2 after rotations. Okay, so these mainly 4 rotations are there. These should be clear, then you can create an AVL tree. Okay, so one more conditions are there, then you will see and for first time, so that will be the problematic. So let me take that example also. So that is the sub problem of this. So I'm just creating one balance tree first. Okay, so like 10, 5. Okay, so like this is 8, this is 3. Okay, and suppose this is 15. Okay, here just think this is a balance tree. Okay, if you count this balance factor, so 0, 0, 0, and this is 0, and this said 2 minus 1, 1. Okay, so you can see this is a balance tree. Suppose if I insert 1 into this, okay, I am just inserting one more node into this. So 1 will
Left
be
of 3.
left of 3.
Left of 3, sir.
So that is I'm just creating new. So 10, 15, and 5, 3, and that will be inserted here. Okay, so 8. If you calculate the balance factor again now, so from the remaining balance factor will as it is, only just calculate the balance factor from new node position which we have just added to the root node. Okay, you need to update this only. So 1 is 0, this side for 3 this will become a 1, for 5 you can see 2 minus 1, so this is also 1, and for 10 this side 3 and this side 1, so this is 2. Okay, now this become a unbalanced things here. So what type of this situation is actually, which type this is there?
L.
LL.
So from check this, which side height is greater? So left side.
Left.
And from child, which side height is greater? Again L.
Left.
Okay. So for LL, we apply the rotation on this node clockwise. Correct? This is the way. Now the thing is, once we will apply this rotation, so 5 will come at this 10 position. Okay, so 5 will come here. Okay, 10 will shift it to this side, 15 will shift it one more, okay, down. Now this, when this 5 will be reached at the 10th position, so this 3 will move up, okay, and this one will also be move one position up. Now this, where this 8 should come actually?
At the left side of the 10.
Yes.
So this is the new situation when you are rotating, but now when this 5 become on the top, but 5 already have the left and this left and right edge, okay, after reaching at that position. But this is the new edge where we should this adjust this. So this will become of a previous node, root node, okay, this position node, as a left child of this here.
Sir, without rotation, how we are doing this?
Without rotations means,
Means here 8 was the child of 5, right?
huh?
Now it's child of 10, as you said, right?
Yes.
So are we swapping at the earlier, means like here 8 is child, right? So are we swapping it to the root and then moving it as the child? Like
That you can in code, you can do in any way. Okay, you can swap this
normally,
or you.
normally I'm saying, is it behind the scenes? Are we doing that to just say that 10 is the left child of root?
No, you will always get the, like, you will always get these things. Okay, what is the pivot position we have where we are applying the rotations? Okay, that node information you already have. Okay, when you are so if you see that if you are rotating right rotation, this clockwise rotation, so this 5 will move to up. So if any child which is up, any child or any subtree as well, if anything is available on this right of this 5, that will be, that you should have to connect on the previous node which was available on the 10 in the left side. Okay,
So
suppose here some x node is also connected. So here for the 10, this will connect it like this x. So this complete part will add as like this. Okay, so what is the means here actually? So this rules are actually designed by AVLs, so that who is the developer of this AVL. After applying this type of connections, you are getting still binary search tree. So that binary search tree property is still maintained
intact.
Okay, you can see all the elements which are coming here is greater than this 5, all are coming on the left are smaller than this, and every parent left and right is also maintained. Okay, so this is one special condition you will see if this situation comes. So just modify like this. Okay, rotations will perform in the same way, left, whatever we have discussed, but this type of connection you have to modify like this.
Sir,
okay,
here how we will decide we have to apply LL or LR or RL?
So we have mentioned based on that how we calculated that balance factor. So we will see which side height is greater. So I think that is the first thing I have discussed.
Okay. Sir, but in this example you have taken the max.
Okay, I'll take one bigger example also. Okay, after that we will see at each step how we will identify. Okay, I hope you got this idea that left is like this situation. Okay, where the height from the balance factor node, which we are getting more than 1, from that node we will see which side height is greater. So if that is greater to the left, then this is the LL situation. If that is coming right, so that is the RR situation. Okay, so for this tree you can see which side height is greater. So right side and then right side. Okay, and another is LR. So for this type of situation you got this. So first, this is the balance factor node where we got 2. Which side height is greater? Left side. Okay, then move to left child. And which side height is greater of this from this 5? Right side. Okay, so that is LR situation. So in this way you can identify it. This is the one additional situation you will get during the rotations. So you have to connect like this. Okay. And similarly, this situation can come in the reverse direction. Okay. So suppose if I create the different things, so like 5, and this is like 20 and 15 and 30. So this is still balanced. Suppose if I add one more element, like 40, so this is now becoming unbalanced. So 0, 1, okay, so 0, this is 1, this is 2, this is 1. Now this is the balance factor. So this is the situation, because this is the node which we are getting balance factor 10. Oh, sorry, 2. From this node, which side height is more, right or left?
Right.
So that R,
Right.
okay, move to the right child of this here.
Right.
From this node C, which side height is more?
Right side.
Right side. So this is the RR situation. So in the RR situation, this is the pivot position, and apply the rotation like this. Okay. And so this 20 will come at the top position to 20, and 10 will move this side, and this 5. Okay. And now with 20, this 30 will also move up, 30, and then 40. Now this side, this part, now which is actually reached at the top position. So left and right is already there. So this part should be connect on the right of the previous root node. Okay, so like this side. Okay, so this is the just reverse of the previous one. Okay, so now this will become a balance. This is the all rule. And one more important thing, so when you will create a one balance factor tree, so you have like this bigger, okay, 3. So when you will calculate the balance factor, so you will see maybe you will get like 2 balance factor here, 2 here, or maybe 3 here, like this. Okay. So in this way, always apply the rotations on the lower one from the bottom. Once you will apply the rotation on the lower one, and you will resolve this part after rotation, automatically above balance factor will also be reduced. Okay. So only after one rotation, just always apply the rotation on the first node which we are getting more than one balance factor from the bottom side. Okay, from the bottom side. So apply the rotation on this part, automatically above balance factor will also be reduced after the rotation. Okay, so this is the one another thing. So now this is the all about the rotations and AVLT. Here now you can take any examples. I'll take the random example. Okay, so I'm just writing the sequence. Okay, so 10, 30, 40, and like 50, and 15, 5, 2, 8, 1. Okay, and like 80. I'm just taking this random sequence. Suppose this is the insertion we have, and we will create a balance search tree using the AVL concept. Okay, for this. So just go step by step and see what type of situation we are getting at every steps. Okay, so you can take any example for your practice as well. So 10, when I'm inserting, this is the first node, 0 balance factor. We will do nothing. So now 10, and then next node 30. 30 is greater than 10, so 30 will insert here. 0 and 1. This is balanced. Now 10, 30, and next node is like a 40. So this is 0, this is 1, this is 2. So which so now we got the 2. So we will apply the rotation here. So what type of situation is this? R. Okay. So this means for this position, apply the rotation. Okay. So after rotation, so 30 will come at the top, 10, and 40. Okay. So now balance factor is 0, 0, 0. This is okay. Now next node 50. This will be added into the balance which we have got after the rotation. So that will be added into the balance tree. So here 30, 10, and 40. So 50 is greater than 30, greater than 40. So this will add here. Okay. So check the balance factor 0, 0. This is 1. And for 30, 1 minus 2, 1. So this is still balanced. Now comes to the 15. Okay. So 30, 40, 50, and 10. So 15 will be add smaller than 30, move to left, greater than 10. So here it will be at, okay, 15. So now check the balance factor. So this was already 0 in the previous example, 1. Okay. Now calculate the this root. So 15 is 0. This is 1, 0 minus 1. And for 30, 2 minus 2, 0. So this is still balanced. So now see 5. Okay. So let's add 30, 10, 40, 50. I'm not sure I'll get 5 here and 15 here. Okay, so 5 will insert here. So 30 is smaller than 30, smaller than 10, then 5 will insert here. So again 0, 0, 0, 1, here 0, 1 minus 1, 0, here 2 minus 2, 0. So this is still balanced. Okay, and then next 2. Okay, so 30, 40, and 50. So 10 and 15, 5, and 2 will come. 2 is smaller than 30, smaller than 10, smaller than 5 here. Okay. So now balance factor for this is 0, 0, 0, and this is 1. This 2 minus 1, 1. Here 3 minus 2, 1. And this is also 1.
Sir,
So
how
still
5 is 1 balance factor?
this left subtree height is 1, right is 0. So 1
Okay,
minus 2,
even
1.
if we have an even if we have a single node, then leaf node, then also the factor will be contributed there. Right?
Huh. Height. Okay, so we are calculating the height only. So single node height is considered as a 1.
Okay.
Okay. So still this is 3. I am not sure I have taken the wrong examples. Maybe so 8. I am not getting any. Okay, 8. 8 will come here. Still height will not be increased. Okay, so let's see. 30, 40, and 50. And then 10 and 15. So 5 and 2. Okay, and now next is coming 8. So 8 will insert. 8 is greater than 30, sorry, smaller than 30, smaller than 10, greater than 5. So 8 will come here. So still it is balanced. So 0, 0, 0, 0, 0, and 2 minus 1 is 1. So 3, 1, 2, 3, 3 minus 2 is still 1. And this is also 1. So not got, okay. Okay, we will get now. So 1. Now we are adding 1. Okay. So see 30, now 40 and 50. So 10, 15, 5, 8, 2. Okay. Now 1 is smaller than 30, smaller than 10, smaller than 5, smaller than 2. So 1 will insert here. So see here, so balance factor for this is 0, this is 0, this is 0, this is 0. Okay. So what is the balance factor for 2? 1. Okay. What is the balance factor for 5?
2.
2 minus 1, 1.
1.
What is the balance factor for 10?
2.
2. Okay, so 3 minus 1, 2. This 40 is also 1. So what is the balance factor for 30? 4 minus 2, 2. So you can see this example, we got the balance factor more than 1 on 2 nodes. So we will solve only this lower part. Okay, from the bottom. Okay, without touching the above one. Above one automatically reduce after the rotation. So okay, check the situation on this 10 1. Okay, so now this is the situation of right side. Okay, from this node 10, right side height is increased, and from 5
Left side
again
height,
the
sir.
right side.
So left side.
Oh, sorry, this is left. Okay, this is the left. Okay, so this is the L situation. So this is the position which we will apply the clockwise rotation on this. So after rotation, you will get the tree update like this. So 40, this will remain as it is. Okay.
5 will.
So here 5 will come. Okay, and then 10 will move this side and 15. Okay, and then 2 and then 1. So what is connected on this? This will become here.
8.
Okay, so you can see we are getting the same situation which we have discussed earlier. So after this rotation, you can see 0 height, 0, 0. Now 1, this is 0. So 2 minus 2, this is 0. and this is 0, this is 1, and 3 minus 2, this is 1. So above 1 is also reduced after this rotation. Okay. So in this way, step by step, this is the process. So one next node is like 80. So I think, okay. So when we will add the 80, so you will see we will get the situation only on 30, 40, 50, and then 80. Okay, 80 will insert here. The remaining will as it is. So 5, 10, and 8, 15, and then 2, then 1. Okay, so this balance factor is not disturbed for the left part, only we have inserted it at this position. So this position, so 0. Now this is 1, this is 2, and on this side, so 3 minus 3, 0. Okay, so this will become 0, 0, 0, 0, 1, 0. Okay, now the balance factor we are getting unbalance on this position. So this is the situation of R. So on this position, apply the anti-clockwise rotation. So this will become 30, and now 50, and 40, and then 80. This, okay, and the remaining part will as it is. 8 and 2.
Sir, where
and
AVL
1.
trees are helpful?
So we are making the balance tree, na? So balance means the height will always be only the one difference you will get in the left subtree and the right subtree for each part.
No, where it is used in practice. That's what it is.
So this is the main example of the binary search tree in the searching data. Actually, database management system also this is used. Okay, so means our binary search tree is balanced. So we can maintain our data in the binary search tree data structure, and at any point you can search and your data in log n time. Okay, and you can insert new element in log n time, and you can delete any element from the log n time. So all three operations can be performed in efficiently log n time if your data is
And
arranged in this way.
read as well, right?
Read is just like a search. So search and insert and delete.
So all CRUD operations easily can be done.
So this is the concept of if our data is, so this is just like a ordered data. So binary search tree is just like maintain the ordered data, like as a binary search tree, binary search operation we have performed on the sorted list. Okay, so this is the structure. So finally we got this is as a AVL tree after inserting all the elements. So you can see how many rotations we got. So first rotation we got in this time. Okay, then second rotation we got at this position. So this was the LL, and third rotation we got on this part. So in this way you will always get one of the rotations which we have discussed above. Okay, and that final version will be considered as a balanced binary search tree or AVL tree. This is also called as a AVL tree. Okay, so this is the overall procedure for the creating a AVL tree. So that provide a balanced, approx balance, not exact balance, but approx balance, where the difference of the left subtree and right subtree will always be smaller than 1 or equal to 1. Okay.
Sir, actually lectures are mentioned about the concept of full binary tree and complete binary tree. So means how it associate within this context of AVL.
That is the different actually type of binary tree. Not this is that is not related here. Okay, so this is not either a full binary tree, not a complete binary tree. So that complete binary tree we have covered in when we discuss the heap actually. So heap is always a complete binary tree. So complete binary tree means if we always fill all the labels actually without skipping any labels. Okay. So suppose if we have the elements of this, so here you can see the first label is complete, second is also complete, third is also complete, and the last label also all the left to right all childs are filled. So this is called as a complete binary tree. Okay, we cannot say that this is complete binary tree. So like this node is there, and then this, and we have kept it like this. Okay, so this is not a complete binary tree because one node is here skipped.
Okay, always it has to be in pair.
So from
and
top to down, yes. all the labels should be filled, and the last label left to right, all child should be filled, position should be
Okay,
filled.
sir. Okay.
Okay, and full binary tree we will generally say is that if our all label are filled,
Means the last event.
last label also, like this. So this is just like a full binary tree.
Understood.
Okay, this is also called as a complete binary tree because this is also satisfying the definition of complete binary tree.
Complete binary.
Okay, but the above one, this which I have mentioned, so this is just like a complete binary tree but not a full binary tree.
Okay. Understood.
Okay. So yeah, this is the AVL tree. So you can take example from your own, any order you can take randomly, and then see what type of situation you are getting. So you will always get a situation from that 4 type of rotations. Then apply that rotations, and you will get a correct AVL tree. Okay. So I hope this is clear. So our slides are also added. That let me see if we have taken any example on that. So here also some only the type of rotations are discussed. So this order is taken. So for one example, you can see this, and so. Okay, I hope you can try this. I think I have discussed all the things, but you will see the situation based on the examples. But you will always get these 4 situations, 4 type of rotations. Okay, so shall I move to the next topic, or any doubt in this? Okay, so code actually you can write in your own way. So for this example, this is a very big code, okay, big implementation, and following the same things, whatever we have discussed. Okay, in some way this is following the same rules. And if you know the concepts of this rotations and everything, you can also write your own implementation. This is just like a step by small. You can divide your problem into a smaller problem and get a full solution. Okay, so generally we not ask code-based questions on this AVL tree, but conceptual question like some order will be given and some question will be asked like what is the leaf node of the final AVL tree. So like this type of. So you should know manually how to create a AVL tree. Okay, conceptually you should know.
Like the one that you did, like, right?
Yes. So whatever. So here this is the long sequence, but in exam maybe you will get a 5-6 nodes. Random like any sequence, and like 3 6 8 2 1 5 like this, and maybe it will be asked like that, create the AVL tree and tell us that what are the leaf node of that AVL tree.
Okay.
Okay, so you have to create the AVL tree for this, and you have to identify the leaf nodes.
So first node will always be, we will always start the first node as root, right? Because that's
So this is the sequence of insertion actually. So 3 will be insert first, then you will add 6. Still this is balanced. So then you will 8. Now this is unbalanced. So 6 will become here, and this is 3,
understood.
8. Okay. Now 2 will be added here. Then 1 will be added here. So now this part will become unbalanced. So you will apply the rotation. So, but always check the unbalanced things by the balance factor. Do not directly put by your own. Okay, and randomly.
Means like if the length increased, whether
So balance factor. So I am just applying the rotation on this part, but I'm not applying this in just by looking the graph. Okay, 0 1 2 and 2 and that 0. Okay, so then I'm applying the rotation on this part. So then it will become 6 and not 6 8 and then 2 and 3 and then 1. Okay, then 5. So 5 will insert 2 greater than 3, then here. Okay, so again see, we got, so what type of balance factor we got? So 0 0 0 1 and 1, and here 2. Okay, so this is the situation L and R.
here we got 2 because 6 to 1, that's 3 node, and 3 minus 1 is 2.
3 minus 1. Okay, so in this situation you can see we will apply the LR situation. So 2 rotations will be applied. So first rotation will be applied here. Okay, and that is anti-clockwise. So 6 8 and this 3 will come here, and 2, and then 1, and this will be 5. Okay, so after one rotation we are getting this. Now next rotation will be applied here, second rotation. So this 3 will come at the top, 6, 8, and this 2, that 1, and this 5 will be here.
Sir, how you identified that two will means like we will swap 3 to 2, right? That's you said, right?
Not, I'm not swapping actually, I'm just rotating, just moving actually in the clockwise direction line.
Okay.
Okay, so in this case LR we required two rotations. So first rotation on the child node, that is anti-clockwise. Okay, so after applying the rotation on this part, just rotate this part, so this 2 will
Okay.
come down. Okay,
2
this part,
comes
so
down, 3 goes up.
yes, so we got this, and the second rotation I applied on this position, that is the clockwise rotation. So this 3 will
That's
goes to
fine.
that position, and then like this.
So left will go clockwise and right will go anti.
Yeah, so this is the LR situation we got. So you will always get this type of one situation, and you have to apply one rotation. After that you will resolve. Okay, and this is the final AVLT. So this is the balance. Actually you will see all balance factors are now more less than 2. Okay, so in this way you need to create a AVL tree. Okay, so this is the one topic, AVL tree, and some theoretical property based questions comes on this. So like, what is the maximum number of nodes for the given height, what is the minimum number of nodes given height. So these are discussed in the lecture also, but you can remember these two formula. This is the minimum number of nodes, okay, that sh equal to sh minus 1 sh minus 2 plus 1, and this is the maximum. So maximum number of nodes is possible, like as if that is the this situation when your tree is full. Okay, like this. So this question is just like a balance AVL tree question. So what is the maximum number of nodes possible for given height? Okay, so here height is given, like suppose h equal to 4. So what is the maximum number of nodes possible? So that is 2 to the power 4 minus 1. This is the 2 to the power h minus. So here yeah, some conventions are there, so always check the base condition given in the question. Okay, so base condition, some books actually you will see that single node, okay, one node, yeah, height is given in the different conventions. So sometimes height is given 0 for single node. Okay,
Yes, root.
root, but sometimes you will see height will be given as a 1 for single node. So in our questions, actually in the exam, we always mention the base situation. So suppose height is given for empty node is 0. Okay, empty tree. So means there is no node and height is 0. That means if we are adding single node, so that height will become 1. Okay, so height is 0 for empty. Then we are adding single node, that height will become 1. If we are adding more like this, so this height will become 2 in this way. So just always check the base condition given in the question itself and then apply your formula. What this? Okay. So here h equal to 4 we have given, we are considering that height is 0 for empty. Okay, we are considering this situation. So for this, how many maximum number of nodes possible? So we can simply 2 to the power h minus 1 we can apply. If height convention is given h equal to 0 for single node, then you have to modify of your formula. Okay, then in that case this will be the height 0 1 2 3. So for 3 height h equal to 3, then you have to apply 2 to the power h plus 1 minus 1, this formula.
Yes, yes.
Okay, you have to change your formula based on the given convention. If height 0 is given for the single node, and then h equal to 3 node, it is asking that what is the maximum number of nodes, you have to apply this formula. Okay, otherwise you have to apply this formula. So means you can logically validate your formula. Okay, so 2 to the power h minus 1, 2 to the power 4 minus 1, that is actually 15. Okay, so this is the maximum. This is in general binary tree property. Okay, binary tree, binary search tree, as well as the AVL tree. So this is the property for all situation. But minimum situation, so means what is the minimum number of nodes So h equal to 0, so that means 0. Okay, so h equal to 1. So if our tree is empty, our AVL tree will be considered as a balanced. With single node, so this is the single node position, this is also a balanced. Actually AVL tree, we can see that this is a single, so that means one node. And after that, for height 2, okay, for height 2, what is the possible AVL tree? So that is just like a uh, like this. Okay, this for height 2, this is the balanced AVL tree. Okay, this is the AVL tree, because balance factor for this is 0, this is the 1. We are looking the minimum number of nodes now. Okay, minimum. So for height 2, 2 nodes are there. Okay, for height 3, what is the minimum number of node possible? So that is like this side single and another side 1, like this.
Sir, how H1 is 1?
H1. So we are looking the minimum number of nodes for given height. So if height is 0, 0 number of nodes in the AVL trees. Okay, AVL tree we are looking, means our tree should be balanced, and we are looking the minimum number of nodes. For height 1, with one node, so this is still balanced, single node, this is balanced. So this is the AVL tree with height 1 with minimum number of nodes. Okay, for height 2, what is the minimum number of node possible in AVL tree? So this is the possible tree.
Yes, sir.
Okay, this is the minimum count, otherwise maximum is this one, 3.
Yes, sir.
Okay, for height 2. For height 3, this is the possible AVL tree. Okay, with the minimum number of nodes. This is the balance actually, 0, 1, 0, 1. Okay, and we are getting 4. So now we got the formula, like how we can get this. So we cannot calculate directly by the given like h10, how we will get the minimum number of nodes 10. So this is the difficult, but this is just like a Fibonacci series type of sequence. Okay, so you will get like the things. So s h, if you are calculating, just check s h minus 1 plus s h minus 2 plus 1. Okay, then you will get a minimum number of nodes for at given height. So if you are looking for minimum number of nodes for h10, you have to calculate like a Fibonacci series. So this is just like a 0, then 1, then 2, then 4. Okay, so this is the 0 height, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so I have written the height here. Okay, just add previous 2 and add 1. So 2 plus 4. So here you can see this is the base case, like in the Fibonacci series, 0 and 1. After that, what we are doing, 0 plus 1 plus 1, 2. Okay, applying this formula. Okay, here 1 plus 2, 3, 3 plus 1, 4. For this 4, 2 plus 4, 6, 6 plus 1, 7. Now next, 7 plus 4, 11, and 1, 12. So this is 19 and then 20. This is 32 and 33. Okay, this is 53, 54.
Correctness of this formula relies on this fact only. No? Anything will be, means, since this is a Fibonacci series, then we are adding 1 to it, more than it. So that means it will exponentially grow.
Yeah, so actually every time, so what we are doing, whatever we have for the height 1, so that was a single node, and for 2 nodes we have this like this. Okay, so we are connecting both these 2 parts by 1 additional node, so like this. Okay, so because of that we are adding 1. Previously,
so this is a rotation, that rotation that you said earlier, it is something similar to that, something different.
No, that rotation is not. We are just only talking about the AVL tree here. So we are just not applying anything rotations here. Okay. So for 2 and 4, so means we got this one and this one. So this is the one part for 4, and this is the 3, and this is this one. So we will take like this. So this is for 2 height, and this complete part as a 3 height.
And then add a top.
And then add 1 like this.
Makes sense.
Okay, so this will become this one. Okay. So in this way, just remember these formula. So for minimum and maximum, that is the simple one, 2 to the power h minus 1 or 2 to the power h plus 1 minus 1. Okay, based on the convention what you are taking. Okay, so these are some basic properties of the AVL tree. So just remember that. Otherwise, the AVL part is done. Now comes to the greedy. Okay, so now greedy, this things is algorithms design techniques. So we have different type of design techniques like divide and conquer. You will see in the beak 8, then DP you will see in the beak 9. So similarly, we have the greedy algorithms. So here greedy, as per the name of this algorithm, greedy. Okay, so means at every steps we always make a greedy choice actually. Okay, to get the optimal solution. So this is just like a need to make a sequence of choice to achieve a global optimal. So we have the one problem and we are looking the optimal solution for that problem. Okay, complete optimal solution. But to solve that complete problem, we are just taking small steps. Okay, at each steps we are always taking the greedy choice to make as a optimal solution or uh, on that steps only. Okay, so sequence of optimal choice. So this is the first definition. So need to make a sequence of, this is also a optimal choice to achieve a global optimal. Okay, so at each stage make the next choice based on the some local criteria, and that is just like a greedy. So you have seen one shortest path algorithm. Okay, so that is the example, it is mentioned here also. So Dijkstra algorithm, Prem's algorithm, Kruskal algorithm, this we will discuss here, but previously you have seen these algorithms. So Dijkstra algorithm, Prem's and Kruskal. So in that algorithm also, one second. So if we are looking any starting node, suppose this is the source node and we have some connected node here. Okay, like this. Okay, so we have the connected node and we are looking the shortest path from this S to like this destination. Okay, we are just finding out the shortest path from S to D. And in this process, Dijkstra algorithm always start from the source node and check what are the adjacent node of this. Okay, and distance are given like 5, 10, 3, 4, 1, like this. So 2, 6, 8, 1, 2, 5. Okay, so each steps when we are looking the S2 adjacent nodes. Okay, so we check what distance we are getting and we also remember the previous distance. So initially we have taken L infinite, okay, for the all and starting for the 0. So S2 this node, suppose this is A. Okay, I have to give a name also, C, D, E, F, and suppose this is the T destination. So S2A, previous distance was infinite, now we are getting smaller than this 5, so we will update by 5. Okay, previous distance by infinite and now S2B is 10, so we will update by 10. So you can see at each steps we are just picking the optimal solution. Okay, so we are finding out the what is the optimal solution we are getting from S to A. Okay, so that we are getting 5. And from S to V, what we are getting the optimal solution in this path. So our final goal is S to T calculation, what is the shortest path from S to T, but in between we are also taking the optimal choice at each steps. Okay, and then we will achieve a global solution for this, global optimal solution for this. So S, similarly after that we will pick the smaller distance node, so that is this one 5, and from this we will check the next update. So from A, now from A to C you can move 3, so 5 plus 3 is 8, so that will be update here, so 8, and from 5 to 1, 6, and previous is 10, so this will be update by 6. So in this process you can see at every steps we are just taking a optimal choice and finally we are getting a global optimal solution. Okay, so this is the things for the greedy approach. So greedy approach, we achieve the global optimal solution by taking the sequence of optimal choice, okay, at each steps. So at each stage make the next choice based on some local criteria, never go back and revise an earlier decision. So this is the one condition for the greedy algorithm actually. So this was the one disadvantage for the digestion algorithm. We never update the previous node which we have already done. So like situation S, suppose A, because of that our digestion algorithm not works on the negative weights. So B, suppose this is given. Okay, so this is the graph, and suppose we have this 3 and this is -2 and this is like a 2. Okay. 3 2. Okay, 1 second. 2. Yes. So what will happen? So suppose if you apply the digestion algorithm on this, now, because digestion algorithm is greedy. Once we have done once we have selected the node, we will never update that node again. Okay. So as we will update, so this is infinite, this is infinite, this is 0. Now S to A is 3, so 3 will update here, and S to B is 2. So oh sorry, this is not this is 2 will update. Okay. So now next, which node will be selected according to the digestion algorithm? That is the smaller one. So 3 and 2, this node will be selected. Okay. So now once we will select this node, we will check from B. Okay. Now we finalize that the distance from S to B is 2. Now we are looking from the B. So from B there is no outgoing edge. So means we have finalized the distance 2 for this B. But after selection this, now we move to the next node. Okay, 3. Because we have already finalized the distance for B, we will not update this now. Okay, so but we are getting smaller distance from A. So from A we got 3, 3 minus 2, we are getting 1. But we cannot update because according to the digestion algorithm, because this is a greedy, we will never update the previous which we have finalized. Okay, so because of that, this digestion algorithms fails on the negative weights. Okay, so here we are getting optimal solution minus 1 on the B if we are coming from S to A and then A to B. But we cannot update because digestion algorithm not allows this. So this is the reason digestion algorithm not works on the negative weights because of this greedy rule property. Okay, drastically reduce space to search the solution. Greedy strategy needs a proof or optimality. Yeah, so this is the important point. Greedy strategy not always a optimal. Okay, we required a proof that this will always work. Okay, sometimes it looks work on the some examples, but that is not always true. So let me give one example to you for the coins problem. So let's you have the coins. Okay, so suppose you have the 10 value coins, like 5 value coins, like 3 value coins, and like 1. Okay, or 2 and 1. So this is the value of coins, and now you have the infinite numbers of the coins for each value. Okay, so I have just given the set of value of the coins with infinite quantity of each coins. Now you have the amount, like suppose if you are looking for 65. Okay, now problem is how you can achieve this amount with minimum number of coins. Any idea, anyone? So 65 is the total amount, and we want to make this amount with minimum number of coins. So how you will get?
Start with the highest derivation.
5 times 6 times 10.
6. Okay, so you are taking 6 times 10. So this becomes
At one time
60.
5.
Now the remaining is 5. So you are taking 1 coin of 5. Okay, so 1 coin of 5. So that becomes 5. So total is 65. Total coins are 7. So this looks correct. Okay, so if you solve any problems with this type of thing, so means what you are doing, you are trying to fulfill the amount by the maximum value coins first. After that, what remaining amount is there which you cannot fulfill by this, then you are taking the next maximum value amount. Okay, so let's suppose if I'm taking any value, say like 47. Okay, so you will take like 4 into 10, then you cannot achieve by 7, remaining 7 by 10, then you will take the next higher, so that is 5. So 1 of 5. Now 2 is remaining, so you cannot fulfill by 3, so but you have to take 1 of 2, and you fulfill, and you're getting 5. So, sorry, 6. So now you feels that this is correct. Okay, and so what you are trying to do, you are always taking the optimal solution, means you are trying to fulfill by the maximum value first. So this is just like a greedy things steps. Okay, and next step again you are taking the maximum value which you can take. Okay, So like now takes the another example for this. Okay, so like you have this 10 or not 10, I'm taking some other things. Okay, like suppose you have the 8 and then 7 and then 6 and then 4, then 2 and then 1, like this. Okay. Okay, now I am trying to making a like a value 25 by this. So what same algorithm you can think here again.
8 into 3 plus 1.
So 3 into 8. Okay, so that 24, now 1 is remaining, so 1 into 1, 1, so become 25. 4 coin. Any better solution this to this?
No, sir.
No.
I think 6 into 4. Was
But still you are
4.
getting the 4, no? 6,
4.
you will
Yes.
get 5. Yeah, that is also not. So this is the optimal actually. Okay, this is the 4 coin is the optimal solution for this. Now you take the 13 actually, amount 13. Apply the same algorithm again. Now you are taking 8 first, highest value. Okay, so you can take only 1. Okay, after that, how much amount is remaining?
4.
4.
5.
5 is remaining. So you can take 1 of the 4, and after that 1 is remaining, so you can take 1 of 1. So you apply the same rule. You are always picking the maximum, but here there is a chance you can take 1 of the 7 and 1 of the 6, and you are getting 13. And here only 2 coins required. And here by the same approach we are getting 3. Okay, so you can see here how this greedy algorithm, which looks good, correct in the initial steps, initial sample inputs, but it fails actually. Here it is fails. Okay, we are getting the optimal solution by taking this 2. So this is not always correct. Okay, because of that this is mentioned, greedy algorithm not always correct. If we are using these algorithms, we require a proof actually. Because of that, prof also discuss some proof for validation. Maybe you can identify some counter examples. So for this problem, we identified this counter example for this 13 amount, which is actually proving that this is not a optimal approach. Okay, so this is the one example for the coins which we cannot solve using the greedy algorithm. Okay, so we require another strategy for this. So this is the same thing. So greedy algorithms not always correct. So this, because of that, this is mentioned. Okay, so these some algorithms which we have used this greedy approach in Dijkstra-Prim's but here we are discussing this interval scheduling algorithm, minimize lateness problem, and Hofmann. These 3 algorithms which we have discussed with the help of greedy, and these all are actually proved algorithms which is solved by greedy algorithm, so correctly. So what is this interval scheduling? So interval scheduling, I hope this problem is clear.
So I have one question here. This interval scheduling minimize lateness and Huffman algorithm. Are these means like primary algorithms in DSA, or they are like where we are applying all these techniques?
So this interval scheduling is just like one standard algorithms, but there is a multiple scenario can be framed on this. So like one scenario professor have already discussed this special video classroom.
Yes.
Okay, so one scenario is already discussed. Similarly, another scenario may be created. So some scenario based questions also asked in the quiz as well as the programming exam. Okay.
So I
So
was
some
thinking it is like more on the implement, means like application of whatever we have learned, but it is
yes,
actually an algorithm.
yes. Okay, so yeah, programming question also asked based on this the OPP exam. So some story will be different, but internally that the same information will be given. So like some intervals will be given, some you have to select some slots like this. You require a maximum or minimum things. So optimal means you are just finding out the maximum something or minimum something like this. Okay, so here we have some slots or we have just a booking request, and after that we want to satisfied the maximum number of requests. Okay, so this is just like a problem which is discussed. So IIT Madras has a special video classroom for delivering online lectures. Different teachers wants to book the classroom. So this is the multiple request we are getting from the different teachers. Slots may overlap. So that overlap problem is okay, so I'll discuss that. Slots may overlap on the time, but we required a maximum number of slots without any overlapping to allocate. Okay, so that is just like a problem we have given some that here you can see this problem. Okay, so let me copy this. So these are just like a request. Okay, so we have this 0 1 2. Okay, this is the first value is just a id. Okay, 1 sorry 1 1 3 and 2 1 5 3 3 4 4 4 5 and 5 5 8 6 7 9 7 10 13 and 8 11 12. Okay, so this is just like a id of this slots. Okay, but this is the starting time, this is the ending time. Okay, so now slots is like if any slots is starting from 1 to 2, second slots is also starting from 1 to 3, like this. So 1 to 5. Okay, and then 3 to 4. So this is starting from here. So 3 to 4. So like this. So you can see 1 to 2, 1 to 3, and 1 to 5 are overlapping actually in the same time duration. So starting time is same and ending time is different. So 1 to 2. So 1 to 3. This cannot be allocated to the one room. So we have only one room, and we want to allocate these slots. So we can, if we allocate this 1 to 2, okay, so 1 to 2 is now reserved, this time slot is reserved. So we cannot allocate 1 to 3 because this starting time is overlapping to this, already something is going on there at this time, so we cannot assign to other on this time. So 1 to 5 we cannot also allocate because this is the starting request, already something is going on. Now 3 to 4, yeah, this is okay because this first activity will be finished at 2, so next activity can be start from 3 to 4. So this is not overlapping. Okay, 5 to 4 to 5, this is also fine. So 1 to 2 is okay, then 3 to 4 is fine, and then 4 to 5 is also fine. Okay, so means any activity is ending on S. Okay, another activity we can start from S. Okay, same time. So that is not considered as overlapping. Overlapping is if any activity is coming at like S value, so if another starting time is less than S. So that is just like overlapping. So our new activity or new slot time should not be smaller than to the previous activity end time, like this. So these are the slots. Now we want to find out the maximum number of slots we can allocate it in this to satisfy it or to make happy to maximum number of teachers to allocate this room. Okay, so how we can do this? So there is multiple greedy approach you can think. What you can think, you can take the smaller number of like duration in this way. What slots have the smaller number of duration, just select first, like this. You can think like this. Okay, whatever the smallest started time, you can select first that. Okay, so you can select this first activity, then what is the next smallest thing, that is 3, so you can select this one. So in this way you can select. So there is multiple way you can think as a greedy, but not all works actually. So that may be fail in some another cases, that may be pass on some cases, but that may be fail also. So here actually for this standard algorithms, in this slot interval scheduling algorithm, if we select the activity based on end time, actually we always pick the smaller end time first, then we will always pick the maximum number of slots. Okay, so what we can do, we can sort our activity of this on this end time in the increasing order, and then we will start picking. So that will always pick the optimal solution. So means here this sequence is given. So we will just sort this all slots based on the end time in increasing order. So means this 0, 1, 2 is the first, then next increasing is 3, so that is fine. So 1, 1, 3. But after that we will not pick this 5. Okay, so next one is this 4. So we will pick this 3, 3, 4. Okay, we will arrange our activity based on the end time in increasing order. So next one is this. So 2, 1, 5, and next is 4, 4, 5, and next is this 5, 5, 8, and so 6, 7, 9, 7, 10, 13, and no, sorry, 12. We will take first that 8, 11, 12, and then 7, 10, 13. So first step is for this to solve this problem, just arrange your all activity based on the this time. Okay, end time. After that, simply pick the activity or this slots request. So this first we will pick the this one. Okay, so 0 to 2. Okay, so this is select. Now when we are picking the next activity, we will check the what is the end time for the last selected activity. If the starting time of that one is equal or greater than to the last time end last activity end time, then we will pick, otherwise we will skip. So here this 1 is smaller than 2, we will not pick this. Now 3 is greater than 2, yes, so we will pick next activity. This one is 3 to 4. Okay, now this is the latest selected. Now again 1, so this one is smaller than 4, not selected. Now 4 is equal to 4, so this will be selected. So 4 to 5, this will be selected. Okay, now next is 5 to 8, so 5 to 8, this will also be selected. Now this 7. Okay, so 7 is smaller than 8, cannot be selected. Now 11 is greater than 8, yes, so 11 to 12. Now this 10 is smaller than 12, we cannot select. Okay, so you can see 1, 2, 3, 4, 5. So 5 activity we have selected. So this is the optimal solution. You cannot found any another combination which is more than this 5. Maybe you will get another possible combination, but that will also be the equal to the 5, but not greater than this. So here we are looking the count, actually we are not finding the activity. So there is a multiple possible way you will get a different possible combination with the same 5 count, but this count is maximum. You cannot get in any way more than 5 without overlapping. Okay, so this optimal solution we are getting. So the step to solve this algorithm is first sort the activity based on the end time in increasing order. After that, select one by one, and every time compare the start time to the previous activity end time. If that is smaller than, skip. If that is equal and greater than, select, and repeat this process. So this is the interval scheduling algorithm. Okay, so this type of problem is also given with slots, and ask that to identify the maximum number of slots. Okay, so that is also asked in the quiz. So it is important, so you should know this process. Okay, so this is the algorithm. So if you see this algorithm,
in brief, can you re-explain the process? Just how to select that particular.
sorry,
Like, what is the base case? Like start time should be less than the start time. Next start time should be less than the final first end time, right?
no. So condition is what activity currently we are looking for. We will check if the start time of that activity is greater or equal to the previous activity end time. Okay, let me explain again. So suppose if we have selected this 1, 2. Okay, so this is the previous selected one, 1, 2. So this is the end time for this. Now if we are looking this for this activity we should select or not. So we
No,
will
we
check
can't.
this one. This is the start time for this to the end time for the
Okay.
previous selected activity.
Okay.
Okay, if this start time is greater than or equal to the previous activity end time,
Hmm.
then we will select, otherwise skip.
Okay. So it should
Okay,
complete. It should complete. Like if we have uh,
so this is
say,
the, if this is less than to the previous one, so means that is this is overlapping actually.
okay.
We cannot pick this.
Okay.
Okay, you can see when we move to 3, so now this 3 is greater than 2.
Mhm.
So because of that, this is not overlapping.
Okay. But 1 to 5 is again overlapping because 3 and 4 comes in between. 4
Ha,
and
so
5
yes.
again non-overlapping. 5 and 8 again non-overlapping.
So this is finishing at 4. Now next is starting at 4. So
Understood.
this is not overlapping.
Okay.
Okay, so this is the condition. So that is taken in the code also. So if you will see the code, so that same condition is actually taken here. So you can see this one accepted.
Mhm.
Okay. So this is the thing. So this is just like a linear loop. So single scan we can solve this. Uh, but initially we required a sorted sort all booking. So because of that, overall complexity will become n log n for this. So we required a sorting on the each activity based on the end time. Then we will just a single scan. So that is overall complexity is n log n for this. Okay. So whatever I have discussed, so same thing is written in the algorithm steps. Now you can write your own implementation for this. So now next problem is minimize lateness. So this is the another type of problem. So here actually some deadline is given for every task. If we are not fulfilling to we are not completing our task before the deadline, so then we are getting some penalty actually. Okay, so that is called as a lateness. So how much we are actually late. So suppose if any activity is finishing and some deadline is given. Okay, so here we have given that some jobs or some activity, anything. So that some deadline is given like 7. Okay, for suppose any activity, and that activity duration time, actually what time that activity will take, so that is also given like 4. Okay, so for each jobs this type of information is given, so that duration or not duration, like burst time I have taken. So how much time that activity will take to complete. Okay, so that is the 4 time. So for each we have given like this, so like this will take 2 and deadline for this is 5, this is take 3, deadline is 4, and uh, this will take 5, deadline is 10, like this. Okay, so this type of sequence will be given for each job. And what is the lateness thing here actually? Okay, so if any activity, so we will start from 0 time, and after that suppose if we are completing this activity as a first activity, so this will take 4 times. So the 0 to 4, this first job is completed, so this is finished at 4. Okay, the deadline was 7, so if we have done before or on the time, so means there is no lateness, so we will just consider as a lateness equal to 0 for that, or we will take another place. Okay, so lateness for this is 0 because we have completed our task before or on time. Okay, so there is no lateness, so 0. And now this is the, like if we have only one machine, we are performing the task. So once this is completed, then we can only start the next job. So we are starting from 2 here. Okay, so this will start from 4. So 4 plus 2, 6. Okay, so this will end on 6, but the deadline was 5 for this. So this job is completing after the deadline. So how much after? So that is 6 minus 5. So that is the lateness value for this is 1. Okay, and now next, if we are picking this, so that will start from 6 plus 3, 9. So that is finishing at 9, but the deadline was 4, so that is much late actually. So that is 9 minus 4, so that is 5 lateness. So this is 5. Okay, so now next is 5. So 9 plus 5, 14, and lateness deadline was 10. So 14 minus 10, that is 4. So lateness for this is 4. So how much our job is actually late to complete? Okay, so this is the lateness for each job. So this is actually different. So here we are getting lateness like this. If you change the order, maybe you will get a different lateness value for the same jobs. Okay, if you change the order to complete. Suppose if you complete this or maybe this first, okay, which have the deadline come, so you will get a different lateness. So this is the lateness for each job. Now our task here is minimize of these lateness. So, so minimize means min of each lateness. So this is 0, 1, then 5, then 4. What? Sorry, not sorry. Max. What is the max value of this? We want to minimize this actually. Okay. So here we are getting maximum of this is 5. But we want to find out some good order. So this value can be minimized in some minimum value. So we are looking the maximum value among all the lateness, and that should be minimized overall by a proper good order. So that we are our goal here. Okay. So this is our one order which we have followed as per the given 1, 2, 3, 4 in the same way. If you follow some different order, maybe you will get some different lateness like 0, 1, and 3 and 2 like this. So here the maximum value is 3. So you can see this 3 is smaller than 5. So what is the minimum possible? This maximize lateness. So this is the problem, minimize the maximum lateness problem.
Sir, and how we will minimize that?
So that is the same type of here. So this is also greedy algorithm. Here we will sort our task based on the deadline based. Minimum deadline we will select first.
Minimum deadline. First, 3
So
and
for
1
the
is there. Then
yes.
1.
So here this is the deadline. So we will arrange our jobs in the increasing order of based on the deadline. Okay.
So 3, 4 will come first.
So let's solve this in the same way. So 3 is the 3, 4, and next is okay. So that 2 to 5, and then that next is 1, 4, 7, 1, 4, 7, and last is 4, 5, 10. 4, 5, 10. Okay. So this is the ID. Just this is the ID, and this is the time required to complete, and this is the deadline. Now we will pick in the same way. So we will start from 0, and then first activity we will start, that will take 3 time. Okay, that will finish at 3. So lateness for this is 0. Okay, if any task is done before or on the time, we will consider as a 0 lateness for this. So 0, and
Sir, how to calculate the lateness? How did you write here the lateness? L equals to 0.
So lateness means what is the end time for this when we have completed this 3 on 3, but deadline was 4.
4.
So we have completed before the deadline. So there is no late actually.
Okay, sir.
This is done before the time. So there is no lateness.
What is it the end time?
This T is the deadline time.
No, that is D. T.
T is the time to complete actually.
Oh, that was
okay. Time to complete.
Okay.
So we have start from the 0 time. Now from this will take 3 time actually. 3 unit you can consider 3 unit time. This will take. So the end time is 3. Now next activity will start on this time 3, and that will plus 2. So that is means end time is 5. So this was the 3, and this is plus 2, 5. So now end time is here 5, and deadline was also 5. So lateness for this is also 0. Okay, we have done on time without late. Now add next 4. So this is 5 plus 4, 9. Okay, and but deadline was 9, that 7. Now we are late, but this is 9 minus 2. Sorry, 9 minus 7, 2. So lateness for is 2. And add 5. So this is 14. and deadline was 10. So 14 minus 10 is 4. So in this way, what is the maximum among all? This is 4. Previously we got this 5. So this is the only way which we can reduce the maximum lateness among all the possible ways. So this is the 4. You cannot reduce more than this.
That means that two people will not be able to submit their assignment as per the analogy that was given.
Yes. But our overall goal is to minimize the maximum lateness among all.
Okay. The earlier one was it was sort and then we.
Yes. So this is the order which you are following, and we are getting 4 maximum lateness. You cannot reduce more than this by any order. Okay. So this is the problem of minimized lateness problem. Means we are trying to reduce the lateness of overall actually. Okay. So if we will reduce this maximum things, means all are actually reduced. So this is the maximum problem. So here the rule is all just take the deadlines and sort these deadlines in the increasing order, and then select this jobs in this order. And this is the formula, like start with 0 and add the time and check if the ending time is less than deadline or equal to deadline or greater than deadline. If it is greater than deadline, just calculate the deadline by end time minus deadline. Otherwise, consider 0. And after that, identify the maximum among all. So that is the solution. Okay.
So, sir, in one of the activity, I think this is the preceding just after the lecture, the last question required that minimization of maximum lateness. So that was the same thing, right?
That's same thing.
Because somewhere it was told that you just have to minimize the lateness. Somewhere it is to minimize the maximum lateness. So they both are.
No, this is just a given name as a minimizing lateness, but this is the meaning here actually. What we are minimizing the maximum lateness actually.
Then I did.
So we are minimizing what we are minimizing. We are minimizing the maximum lateness among all lateness. So this is the main problem. Okay, somewhere you will get this thing minimizing lateness. That's the same thing actually. So activity problems, I think some questions are given.
Yes. That third, fourth.
So all are actually same things. Do not confuse on this. So this is I maximize the. So this is just like a theoretical question, but this is a practical.
A greedy interval. These are just mix of both, right? Both.
These are all actually scheduling algorithms. Okay.
I think it was the last question.
This one? This is I think minimized maximum lateness among all lateness. So this is the same actually clear definition. Otherwise, it creates a confusion.
Move a little better. No. I want to see the previous questions. Yes, these type of questions.
So this is also this is not just like a same problem, but this is also a greedy problem. So here we have to find out the minimum number of rooms. So that how you.
I think it's scheduled like the earlier one that you showed.
This is not a scheduling algorithm as well, but yeah, you have to identify that how you will solve this. So this is just like a naive solution. You have to make sure that which room is actually become empty or like this. So this is. Let me get the pen.
No, they have given as X and E, right? So it is almost similar.
But here the information is different, na? So we are just finding out the minimum number of rooms here. We are not selecting the slots.
Yes.
Okay, so we have to take the rooms, like we are just taking the first room and we are allocating like this A activity. Okay. Now we are following this order to complete. As first room is booked by A, it is not finished. Some noise is coming. Can you?
S is the starting and N is the
Ha.
ending.
One second. I think Porindu, you are some noise are coming. Yeah. Okay, I'm explaining first, and then you will open your mic and ask. So starting time S, end time is end, but this is just like an order actually. Okay, so AS is started and BS is started, but AS is still running. So like this is the time chronological order. So now one room is booked by A. It is still running. At the same time, we got the next activity. Okay, so next activity B. So we cannot give that room because A is still running. So we have to definitely give the another room B at the same time. Now both are running. C activities come. So we have to give definitely the third room C. Okay. Now A activities end. So this become empty. So when we are getting next activity, so we will not create a new room. Now A first room is become empty, so we will allocate to that D. Okay, in this way. So E is now new activity. Now all three are utilized. So that fourth we have to create. So for E. Okay, now C is completed here. So B also completed. So 2 and 3 is now become empty. Next activity is coming, so we can allocate to any. So like F. So D. Okay, so D is also finished. Now G is coming, so we can give of any. Okay, so the G we are giving. So H still one is khali. So this H is done. E is finished. Now F finished. Now G finished. Now H finished. So in this process, how many rooms we have taken? So only 4. So this is the minimum number of rooms we have taken in this process. So this is the minimum things. So here we are not selecting the slots, but we are just taking that what minimum number of rooms we can satisfy all this sequence of like in incoming activity and end activity. So this is another type of greedy algorithms, and you can solve like this. Okay.
Understood, understood, sir.
Yeah. So this is the greedy, and last problem is discussed. That is that Hoffman codes. So that is also important. So Hoffman codes. So Hoffman codes problem is also very real life problems we generally solve in the networking. So that is create the codes actually Hoffman codes for to reduce the bits to transform. Okay, to transfer. So what happens generally if we are using any coding technique? So we take the fixed length of the code. Suppose we have the 5 character like A, B, and C, D, E. Okay, if we have the 5 character and we have the different frequency for each character. Like suppose A is repeating 100 times, and this is B is repeating like 3 times, and this is repeating 50 times. This is 10 times. This is 2 times like this. Okay, so this is the overall number of frequency we have. So if you add all this, so you will get a total 165 character. Okay, but if you're taking any fixed length code for this, suppose if you're taking like 4 bit for each. Okay, so how many total bits is required to transform the message of this 165 characters? So that is simply 165 into 4. Okay, so that you will get how much? Okay, so that is like 0 and 24 and 6 to this is 4 into 6. Okay, so 660 bits are required if you are following these things. But how we can reduce this bits, because the network actually bandwidth we have limited. We want to reduce the number of bits to transfer the message, so that will take less time to transfer. So how we can take the coding in different ways? So that is the concept of Hoffman coding comes, and this is generate the prefix code. Hoffman codes generate the prefix code, and I'll explain that what is this prefix code means. So how this Hoffman code algorithm works on this type of frequency, and how this greedy algorithm actually be used on this, and we will see how we can reduce overall number of bits. Okay, this way. So let's take the example for this. I'm deleting this 660. So I'm taking the example like the same way: A, B, C, D, E, F. Okay, I'm taking different example F. So like this is 100, this is 50, this is like 5, this is 2, this is 3, and this is like 70. Okay, I'm taking randomly. So this frequency are given. So how Huffman algorithm works and how Huffman algorithm generate the codes. Okay. So first thing, Huffman algorithm is actually we takes the frequency, always we takes the two smallest frequency first, and then we build the tree from bottom up manner. Okay, so we creating a Huffman tree first. After that, we will create a Huffman codes. So here, what are the codes we have initially? So that is the actual frequency which we have given. So what are the two smallest ones? So this 2 and 3. Okay, so this is the actual frequency of character, given character. So we can just add this. So D is 2 frequency, or you can take like 2 and 3. So this is the actual frequency I'm writing as a like this square box. This will be considered as a leaf node, and we'll add this. So what value we are getting after adding that, I'm writing into the round bracket. So that is the internal nodes. So this 2 is representing D and this is representing E. So now we have the new frequency. So this is 100 and this is 50. This is the original frequency 5, but now this 2 and 3 have already done. So I am just writing 5 as a internal node here and 70 for this. Okay, so now this is the remaining weights we have. Again we will pick the same two smallest one. So 5 and 5. So this 5 is already available in the tree, and this is the actual frequency. So we will just make on the left or right, you can make in any side. So I'm just writing 5 here. So this is representing the C frequency. Okay, and we'll add this. So this is 10. Now we have the remaining frequency like 100, 50, and then 10 and 70. Okay, so what are the two smallest ones? So this 50 and 10. So 10 is already there. So this is the calculated one, and 50 is the actual. So that I have written 50 here. So we'll add, and this 50 is B, and this becomes 60. So 100, and then this becomes 60, and then 70. Sorry, not this one. So now 60 is already there, and we will select two smallest, 60 and 70. So 70 will come with this, and add this is 130. Okay, so now 100 and 130. So two smallest one, this one. So 130 is already there, so you can put 100. Okay, so like this is 230. So this is become a total number of characters we are also getting here. So 230. If you add all this, you will get a 230 count. Now this become a Huffman tree. Okay, so here you can take into the left or right. In general, sometimes we always take the smaller frequency on the left. If we are getting suppose 10 and 50, so this 50 is greater than to the 10, so we are taking on the right. But if we are getting a smaller one, then generally we takes on the left. But that not change anything actually. So that will give it different codes, but that is also correct. So here we have created a Huffman tree by this greedy approach. So what is greedy here? We are always selecting two smallest one at each steps. Okay, so that is the greedy choice actually at every steps. Now how the code is actually generated? So code is generated, just mention 0 on the left edge and 1 on the right edge every. Okay, 0 1 0 1 0 1 0 1 like this. Okay, now for each character, because each leaf node are representing the actual frequency. So this was F and this is the A. Okay, so I am just writing the frequency code for each B, C, D, E, F. Okay, so what is the, so just traverse from root to that leaf node and see what sequence are coming on the edge. Okay, so from this root node, okay, to this A, we are getting only one. If you are coming to B, so you have to come through this path. Okay, so this path. So 0 0 1. So just traverse the edge. What edge value you are getting, just write that. Okay, now C. So for C you have to come from this this one, this path. So 0 0 0 0 0 0 1. For D you have to come completely this left. Okay, so 0 0 0 5 times. and then E you have to come 40, and then this is 1, and for F you are coming 0 1. So these are called as a Hopman codes. Okay, first step is generate a Hopman tree. After that, generate codes. So these are called as a Hopman codes. So here lengths are different for each. Okay, so here length is 1, here length is 3, here length is 4, here length is 5, here length is 5, here length is 2. So if you see the pattern, now you will see whatever for character which we have the more frequency, we are getting the less length code for that. Okay, so for 100 frequency, we are getting only one length code. For next, this 70, we are getting two length code. For B, which we have the 50, we are getting three. And for the smaller frequency, we are getting the big length. Okay, so this is the Hopman codes. And if you calculate the total frequency, so here 240, all the complete character 230. So 230 are there. So if you follow the 4-bit length code for this, so you will get a like 2 and 4 to the 8 and 9. Okay, so 920 bits. But if you follow this, so you will get a less number of bits for this. So A is 100, so 100 into 1 plus B is 50, so 50 into 3 plus, and F is 70. Sorry, let's continue. So C is 5, so 5 into 3, 5 into 4 plus D is 2, so 2 into 5 plus 3 into 5 plus that E F, sorry, 70 into 2. So this number of bits we are getting. So 100 frequency with one length. So 100 plus 150 plus 20 plus 10 plus 15 and plus 140. So how many you are getting? So 250, 270, 280 and 280 and 100, 380, the 420 and 435. So 435. So you can see we are getting, if we are creating the total codes length for the by this Hopman codes, we are getting only 435 bits required for this instead of 920. So in this way, we are reducing our total bits, and this is the Hopman codes. And what is the prefix code means here? So prefix codes means if you see each code, so no code is coming as a prefix of another code. Prefix means the complete code will not come as the part of initial code of any other. So here you can see 1. So 1 is not coming as a initial start from starting in any another code. So if you see 0 1, 0 1 is also not coming in any code at the starting. Okay, so any smaller code is not coming completely as a prefix of any other code. So that property is called as a prefix property. So that is because of that we are saying this is a prefix codes. Okay, so main codes are always prefix code. So this is the one property. Because why this is not happening? Because we have the unique path for each root to leaf. Okay, so prefix will only come if we are getting the code in between in the path, then it will come, but that is not the case here. Okay, so we have the unique path from root to leaf, and that is the Unicode. So this is the Hopman code. So this is the process. So first generate the Hopman tree and then generate the Hopman codes. So questions are asked like this. So you will get a frequency or probability. So means you will get some characters A, B, C, D like this. Some frequency will be given either in the form of value, simple integer value, or maybe some probability like 12.5, 13 point like this. Okay, so in this way, but apply the same rule, Hopman code algorithms rules. So always pick the 2 1 and combine that and generate this Hopman tree, and after that mark 0 1 on the left right. Okay, each left as 0, each right as a 1, and then generate the codes. That question will generally ask like this code of this A or B, C, like this, length of the code, average of the code's length, like this. So this in this way. So this is the process to solve this Hopman code problems. Okay, any doubt in this?
Sir, can you explain the Hoffman tree building again?
Okay, so let me take the another example. So A, B, C, D, E, F, G, like this. Okay, so I'm taking another like 10, 20, 5, 2, 30, 100, and 15. Okay, so like this, in this way. So you will get this type of information. Maybe in the simple integer value you will get some probability, like, okay, so probability is just like a one value, so you will get 0. 0.1, 0. 0.5, 0.2, like this, in this way, but some value will be given. Okay, so you have to create a movement tree for this. So each steps, initially you have like this 7 bits. Okay, so pick the two smallest one
Okay.
and create a movement tree for from bottom to up. So like this is 2 and this is 5.
Yeah.
Okay, so 2 is for D, just mention this, and 5 is for C, and combine this. 2 or 5, 7. Okay,
Okay.
now this is already done, so 2 and 5 are done. Instead of this we have get 7, so 10. So this is become internal node, so we will just mark in our next list 20 and 30 and like 100. Just maintain this table in the another side and create a tree on another side. Okay, so 15. Next two smallest one,
10 and 20.
no, including this 7.
Oh,
Okay, 7 and 10.
yeah.
So just mark. Okay, 7 is already there, so
Yeah.
you are taking 10. So just keep this 10 with 7. Okay, 10.
Okay.
So now you are getting, so 10 is representing A, and this becomes 17. Okay, so
Yeah.
10 and 7. So just mark this 20 and 17 and 30 and 100 and 15. Okay, next two smallest one,
Um, 17 and 20.
15.
Okay. Yeah.
Okay, just maintain that. So I'm just writing 15 here, so 15, and this is G, and just like this, so 15 and 17 is 32. Okay, so next is like 20 and 17. This is already done, so this was also taken. Huh. So this 20 and then 17 and 15 we have taken, so this is now 32. So 32 and 30 and 100. Okay, so what are the next two?
20 and 30.
Huh. So this time you can see both are new.
Yeah.
Okay, both are new, so we have to take separately both actually. Okay, so just create from here, because that sum will come at the same level of 32, or you can create from bottom, but you will get a long edge for this. So 32 and sorry, 30 and 20. So 30, or let 20 here and 30 here separately. Okay, so this 20 is for B, and this 30 is for E.
Sir, why
Now
we are separating here?
because we have totally new separate smaller one that is representing the frequency, so we cannot combine, na?
Yes.
Previously we have combined because one value was coming from the already that was mentioned in the tree, and one was coming from the new node, but this time both are coming separately, new node actually, new frequency. Both are not exist in the tree, so we have to create a separate tree for that. Okay, so now this 20 and 30 become 50. So now this 50 is in internal node, so that is 50 internal node, 32 is also internal node, and 100 is still frequency. So next is 50 and 32.
Yeah.
So both are in already in tree, so just add this. Okay, so 82. Okay, now 82 and this is 100, so 100 is still a frequency. So now we will combine this, so 100 will become a leaf node, so that is actual frequency of this is F.
100 and
Okay, 182.
180.
Okay, now just mark 0 1 0 1 0 1 0 1 0 1 and 0 1 like this, and generate the code. So A, B, C, D, E, F, G. Okay, so for A, so for A is here. Okay, so here just traverse 0 0 1 1.
A.
Okay. For B, B is here, so 0, 1, 0. C is here, so 0, 0, 1, 0, 1. Okay, D is here, so 0, 0, 1, 0, 0. E is here, so that 0, 1, 1.
Yeah.
And F is 1. And G is here, so 0, 0, 0. Okay, so these are Hoopman codes.
Okay.
Okay,
Yeah.
so in this way, after that question will be based on some this information, so you can just figure out.
Okay.
So this is the Hoopman tree and Hoopman codes. Okay, so yeah, this is the last topic of week 7. So if you have any doubt, you can ask. Okay, any query?
So
No, sir.
interval scheduling, I have some doubts.
Haha, okay, tell me.
Can you explain this?
What doubt you have?
So next step process I think I have some steps problem. I didn't know, but I have. I want to clarify it again.
Do you have any doubt in any question, specific question, or you are not able to understand the problem?
I'm not able to understand that. I'm not.
Questions you are not able to
No,
understand?
no, no, no. There is no questions. I didn't have solved any questions till now.
Okay. So we have already discussed this algorithm in detail. Have you seen this in this session?
Yes, sir. I
Okay, but still you not get this.
I have missed this one.
Okay. Can you rewatch again, because we have already discussed in details with
Okay,
examples.
okay, sir.
So that will be the complete repeat actually.
Okay, sir. I will complete it.
If you missed, then you can watch again. Okay. Otherwise, you can ask in the next session or maybe.
Okay, sir.
Okay. Any new doubt? Any specific doubt? Okay. Okay, then if no doubts, then we can wind up the session. Okay, just practice on that and join the TA session if you have any doubt in any specific topic, and also practice on the problems and solve questions. Okay. Okay, then thanks. Thanks everyone. Bye. Good night.